Our reality might be a convincing and beautiful illusion. The space you see and move through every single day, defined by length, width, and height, could be just a thin slice of a far grander cosmic structure. This is the search for hidden dimensions beyond our three-dimensional reality, one of the most profound enigmas in modern physics. By the end of this journey, you will understand how this quest could completely rewrite the rules of the universe, from the forces that hold atoms together to the ultimate fate of the cosmos. What if gravity is weak because it is leaking into places we cannot see? And could the Big Bang have left echoes of higher realms in the oldest light in the sky? This expedition will take us from the elegant equations of a forgotten genius to the colossal machines shaking the fabric of space, all to answer a single haunting question. How much of reality are we simply incapable of perceiving? To a being living entirely on a flat sheet of paper, your hand reaching down would be an incomprehensible miracle. First, they would see only a series of disconnected circles, strange shapes appearing and vanishing without cause, a reality governed by rules that seem to make no sense from their limited perspective. This is the power of the classic thought experiment Flatland, a story that perfectly frames our own dilemma. We are the Flatlanders, confidently navigating our world of length, width, and height, yet potentially oblivious to realms that exist just beyond our perception. The journey to uncover those realms began not with telescopes, but with pencil and paper in the 19th century, with a mathematician named Bernhard Riemann. He gave us a new language, a way to describe spaces that were not flat and static, but could curve, twist, and exist in more than three dimensions. His work was a quiet revolution, a set of tools waiting for a universe to describe. That universe arrived with Albert Einstein. His general theory of relativity did something astonishing. It proposed that gravity is not a mysterious force pulling across empty space, but the result of mass and energy curving the very fabric of a four-dimensional reality. Time itself was woven into this fabric as the fourth dimension. This was the first great crack in our three-dimensional worldview. Space was no longer just a passive stage where events played out. It was an active, dynamic participant, bending and shaping the paths of everything within it. If our reality could be described as the curved surface of a four-dimensional object, a profound and haunting question naturally followed. What if our entire four-dimensional spacetime is itself just a surface, a membrane, floating within a reality of even greater depth? Einstein's curved spacetime masterfully described the dance of planets and the bending of starlight, painting gravity as the grand architect of the cosmos. But descend into the realm of the vanishingly small, and this elegant picture shatters into a storm of chaotic probability. Here, in the quantum world, particles pop in and out of existence, communicate instantaneously over vast distances, and behave as both waves and solid points depending on how we look at them. The rules governing this subatomic domain are captured by a different masterpiece of physics called the Standard Model. It is a framework of breathtaking precision, predicting the behavior of particles and forces with accuracy down to many decimal places. Yet for all its power, it holds a profound and glaring omission. The force of gravity, so dominant on cosmic scales, simply does not fit into its equations. It is the one puzzle piece from a different box, leaving us with two spectacularly successful but utterly incompatible descriptions of reality. One governs the very large, the other the very small, and they speak completely different languages. This fundamental conflict is the great unsolved problem of modern physics, a schism at the heart of our understanding. And it is this very conflict that makes the search for hidden dimensions not just a curious side quest, but an urgent necessity. Could these unseen realms be the missing link, the common ground where gravity and quantum mechanics finally shake hands, the most promising candidate for such a unification emerged from a radical reimagining of what matter truly is. What if the fundamental particles of the universe, the electrons and quarks we think of as tiny dots, are not dots at all? Imagine instead that at the smallest possible scale, they are incredibly tiny, vibrating loops of energy like minuscule rubber bands. This is the core idea of string theory. The mathematics of these vibrating strings are beautiful, but they come with a startling requirement. For the equations to remain consistent and avoid mathematical chaos, they cannot describe strings dancing in just 3 dimensions of space and 1 of time. The numbers only work, the music only stays in harmony if the universe has more room to breathe. The theory demands extra dimensions, often 6 or 7 more, folded and hidden away at scales so infinitesimally small, they have so far escaped every instrument we have ever built. This isn't a whimsical addition, it is a mathematical imperative. The search for a single, unified theory of everything therefore transforms into a cosmic treasure hunt. The prize is not just hidden dimensions for their own sake, but the elegant framework they promise, one that could weave all of nature's forces, from the might of gravity to the glue holding atoms together, into a single, coherent tapestry of explanation. The year was 1921, and a physicist named Theodore Kaluza was staring at the most beautiful equations in the world, Einstein's description of gravity, and he saw something no one else had. What if, he wondered, the universe was not 4-dimensional but 5-dimensional? He took Einstein's own work and wrote it out for a reality with 1 extra, unseen dimension of space. The mathematics was stunningly elegant, but the result was even more profound. From the geometry of that 5th dimension, a new set of equations emerged perfectly describing not just gravity, but the other great force known at the time, electromagnetism. In one breathtaking stroke, Kaluza had suggested that the forces of nature were not separate things at all, but different facets of a single, higher dimensional reality. It was as if you had only ever seen the shadow of a spinning coin, a blurry oval moving back and forth, and you invented 2 separate laws to describe its length and its motion. Then someone shows you the coin itself, and you realize both shadows are cast by one simple, rotating object. The extra dimension was that coin, the true object casting the shadows we call physics. But this immediately raised a practical, almost humorous problem. Where is this 5th dimension? Why can't we walk into it? The brilliant refinement came from Oscar Klein. He proposed the dimension wasn't missing, it was simply hidden, curled up into a circle so incredibly tiny that even a single atom would be a giant galaxy in comparison. Think of a long, thin garden hose seen from a great distance. It looks like a simple 1-dimensional line. Only when you get very close do you see its circular cross-section, its 2nd dimension, always there but invisible from afar. Our entire universe, Klein suggested, could be like that hose. We perceive the 3 large, expansive dimensions, but at every single point in space, there is another dimension curled into a loop 1 billion trillion times smaller than an atom. This idea of compactification became the foundational blueprint for all future theories of hidden dimensions. Kaluza and Klein's work was a quiet revolution. It told physicists that the search for a unified theory was not about inventing new particles or forces, but about discovering the hidden geometry of reality itself. The different notes in the symphony of the cosmos, from gravity to light, might just be different vibrations of a tightly wound, unseen string. Kaluza and Klein's vision of a single, hidden 5th dimension was a masterstroke of elegance, but the universe, it seems, has a taste for more elaborate symphonies. The next great leap came from a radical reimagining of reality's most basic building blocks. Forget points or particles. Picture instead a universe woven from unimaginably tiny, vibrating loops of energy. These are the fundamental strings of superstring theory. Their behavior is everything. Just as a single violin string can vibrate in different modes to produce a cello's deep hum or a flute's high pitch, these cosmic strings vibrate at distinct frequencies. One specific pattern of vibration might manifest as an electron, another as a quark, and yet another as the particle carrying the force of gravity. In this breathtaking picture, all matter and energy in the cosmos is not a collection of disparate dots, but a grand, unified composition played on these microscopic strings. For this cosmic music to be in tune, however, the stage must be set just right. The mathematics governing these vibrating strings are exquisitely precise, and they only remain consistent, avoiding fatal contradictions, if the universe provides them with more room to perform. The theory demands not 1 but 6 or 7 additional spatial dimensions, bringing the total to 9 or 10. This isn't a suggestion, it's a requirement for the entire elegant framework to hold together. Alongside this dimensional expansion comes another profound concept called supersymmetry. It proposes a deep, underlying partnership in nature, where every known particle of matter, like an electron, has a hidden, heavier twin particle that carries force. This elegant pairing would beautifully balance the quantum equations, but it also implies a whole shadow population of particles waiting to be discovered, each a whisper from the higher dimensional geometry. So where are all these extra dimensions? Why don't we stumble into them? Following Klein's blueprint, they are thought to be compactified, curled and folded upon themselves at every point in space into intricate, multidimensional shapes known as Calabi-Yau manifolds. The geometry of these hidden shapes is not arbitrary. It acts like the internal wiring of a cosmic instrument. The specific way a Calabi-Yau manifold is folded determines how the strings within it vibrate, which in turn dictates the properties we observe in our three-dimensional reality. The number of particle families, the strength of forces, even the existence of the electrons that power our world, could all be frozen accidents of this hidden geometry. This leads to a staggering, almost unsettling implication. If many different Calabi-Yau shapes are mathematically possible, then our universe, with its specific laws and constants, may be just one possibility in a vast landscape of potential realities, each with its own unique physics blooming from a different hidden shape. The search for dimensions becomes a search for the reason our particular melody was played. But the strings of superstring theory require a stage, and the most elegant one we have imagined is a realm of tightly curled, microscopic dimensions. Yet there exists an entirely different, and perhaps even more radical, framework for where these hidden realms might be. What if the extra dimensions are not curled up at every point, but are instead vast, even infinite, and we simply cannot access them because we are trapped? This is the Brane world scenario, and it begins with a powerful shift in perspective. Picture our entire three-dimensional universe not as a solitary island, but as a thin membrane, a three-dimensional sheet, floating within a much larger, higher-dimensional space called the bulk. In this view, we are not free to move in all directions of this grander reality. Every star, every planet, every one of us is stuck to the surface of our brain, like characters printed on a page. The familiar forces of nature, like electromagnetism and the nuclear forces, are like inks or glues that bind particles to this page. They cannot leave the surface. But gravity, according to theorists like Lisa Randall and Raman Sundram, is different. It is the one force that can seep into the bulk, leaking off our membrane and into the higher dimensional space around us. This single, elegant idea solves a century-old mystery. Why is gravity so unimaginably weaker than the other forces? A magnet can lift a paperclip, effortlessly defeating the gravitational pull of the entire Earth. In the Brane world picture, gravity appears weak to us not because it is inherently feeble, but because its true strength is diluted as it spreads out into the extra dimensions. We only feel a faint shadow of its full power, the tiny fraction that remains on our brain. This framework shatters the old assumption that all extra dimensions must be microscopic. If only gravity probes the bulk, then these dimensions could be surprisingly large, perhaps even infinite in size, and we would never casually stumble into them. Our entire cosmos could be one of many parallel branes, floating like sheets of paper in a multidimensional wind, each with its own stars, its own laws, perhaps even its own versions of us, forever separated by a gap we cannot cross. This transforms the experimental search in a dramatic way. We are no longer just looking for the subtle tremors of tiny, curled-up spaces. We are now hunting for particles that might occasionally, through a rare quantum fluctuation, hop off our brane and vanish, or for telltale ripples in gravity that betray the presence of a neighboring universe just a millimeter away in a direction we cannot point to. The brane world turns the hidden dimensions from a mathematical curiosity into a potential cosmic neighborhood hiding in plain sight. Geometry is the silent language of reality. While we perceive a world of objects and forces, physicists and mathematicians listen for the deeper grammar written in the shapes of space itself. To understand hidden dimensions, we must learn to speak this language, a dialect that uses tools from differential geometry and topology to model realms we cannot see. Think of it this way: if you only ever looked at flat shadows, you would invent a physics of lines and ovals. But to understand the objects casting those shadows, you need the mathematics of spheres, cubes, and cylinders. The search for extra dimensions is that leap from studying shadows to deducing the true, higher dimensional forms. The central concept is compactification. This is the idea that extra dimensions are not expansive highways we can travel, but are instead curled and folded at every point in our familiar space. The simplest example is a dimension curled into a circle, unimaginably tiny. At each location in our three-dimensional world, there is a loop so small that moving along it would bring you instantly back to your starting point, like an ant walking around the circumference of a filament in a light bulb. But the mathematics allows for far richer possibilities. These hidden dimensions could be curled into spheres, donut shapes, or the exquisitely complex forms known as Kaluza-Klein manifolds. These are not shapes you could sketch easily. They are six-dimensional landscapes of twisting, folding space with holes and tunnels defining their topology. The specific geometry of this hidden landscape is everything. Within these curled-up spaces lie what theorists call moduli. These are not particles but parameters, like the dials on a cosmic control panel. One modulus might set the overall size of a curled-up dimension. Another might describe the degree of its twisting. The incredible idea is that these moduli could have been dynamic, fluctuating fields in the fiery moments after the Big Bang. As the newborn universe cooled, these parameters may have settled into specific, stable values, like a rolling ball finally coming to rest in a valley. Where it stopped determined the geometry we are stuck with today. This is a profound shift in thinking. The laws of physics are not handed down on a tablet. They could be frozen accidents, the result of how the hidden dimensions crystallized as the cosmos expanded and cooled. And this geometry is not just abstract mathematics. It directly writes the rulebook for our three-dimensional reality. Imagine the hidden Kaluza-Klein manifold as the resonant chamber of a cosmic instrument. The way it is folded determines the possible vibrational frequencies of the strings within it. One specific frequency might correspond to an electron, giving it its precise mass and charge. A different fold in the geometry might make the strong nuclear force a bit stronger, or create three distinct families of particles instead of two or four. In this view, every constant in nature, every fundamental property of matter, is a direct translation of hidden geometric detail. The search for these dimensions, then, is not a hunt for mere curiosities. It is the search for the architectural blueprint of physical law itself. We are reverse engineering the universe, trying to deduce the shape of the hidden workshop from the finished product we see around us. The question that follows is both thrilling and daunting. If the geometry could have settled in many different ways, could our universe, with its life-friendly constants, be just one possibility in a vast cosmic landscape? The geometry of the unseen may dictate the laws of nature, but how do we test a blueprint we cannot read? We must look for a signature, a crack in the familiar world where the hidden architecture shows through. Our most promising tool for this search is also the most mysterious force in the cosmos, gravity itself. In 1798, the scientist Henry Cavendish performed an experiment of breathtaking delicacy. Using a torsion balance with lead spheres, he measured the faint gravitational tug between ordinary objects, effectively weighing the Earth. For the first time, humanity had quantified the strength of gravity. Yet that measurement revealed a profound puzzle. Compare gravity's pull to the other fundamental forces. The electromagnetic force that binds atoms and powers our technology is stronger by a factor of 1 followed by 36 zeros. Even the weak nuclear force, which governs radioactive decay, is a trillion times more powerful than gravity at the subatomic scale. This is not a small discrepancy. It is the most extreme hierarchy in all of physics. Why is the force that holds galaxies together, that sculpts the cosmos, so unimaginably feeble at the level of particles? The answer may lie not in gravity's nature, but in its reach. If gravity alone can leak into the bulk of higher dimensional space, as Brane world models suggest, then its true strength is not what we feel. Imagine a powerful light bulb placed at the center of a vast, dark sphere. An observer on the inner surface of the sphere sees only a dim glow because the light's brilliance is diluted across the enormous area. Our three-dimensional universe might be just such a surface. We experience only a faint, three-dimensional shadow of gravity's full, multidimensional strength. This elegant idea makes a startling, testable prediction. In our familiar world, gravity obeys Newton's inverse square law. Double the distance between two objects, and the gravitational force drops to a quarter of its strength. This is a hallmark of a force propagating through 3 dimensions of space. But if gravity is spreading into extra, large dimensions, its behavior should change at very short ranges. As two objects are brought incredibly close together, within a fraction of a millimeter, the force should begin to deviate from the inverse square law, becoming slightly stronger as it taps into the full geometry of the hidden realm. Detecting this deviation has become one of the most delicate challenges in experimental physics. Teams around the world use apparatuses that would make Cavendish marvel. Exquisitely polished gold-coated plates, thinner than a human hair, are suspended microns apart. The gravitational attraction between them is measured using micro-cantilevers, devices so sensitive they can detect a force 1 billion times smaller than the weight of a snowflake. These are not colossal machines, but miracles of miniaturization and isolation, operating in vacuum chambers and shielded from the slightest vibration or electrostatic whisper. They are hunting for a departure from classical physics over a distance smaller than a dust mote. Finding it would be a revolution. It would mean that our most familiar force, the pull that guides a falling apple and anchors planets to their orbits, is our only direct line into the hidden dimensions. Gravity would cease to be merely the architect of the large-scale cosmos. It would become our most precise probe of the invisible, a fundamental tremor revealing the true, vast shape of reality. While gravity experiments listen for a faint whisper in the dark, other efforts take a dramatically different approach. They attempt to shout into the void and listen for an echo. This is the realm of the particle accelerator, where the search for hidden dimensions becomes a matter of immense, concentrated force. At facilities like the Large Hadron Collider, protons are whipped to within a hair's breadth of the speed of light and then slammed together with cataclysmic energy. These collisions recreate, for a fleeting instant, the searing conditions of the early universe. Think of it not as simply breaking things apart, but as violently shaking the very fabric of space-time itself. If that fabric is woven with extra, tiny dimensions, such a tremendous jolt could theoretically set them ringing. It could excite vibrations in those hidden, curled-up spaces. The key is knowing what to look for in the aftermath of the microscopic firestorm. When two protons collide, their energy is transformed into a spray of new particles, all captured by layers of sophisticated detectors. Physicists know the precise energy and momentum the protons brought into the collision. The law of conservation dictates that the energy of the debris flying out must equal the energy that went in. This is their forensic ledger. Now, imagine if one of the particles produced in that fireball was a graviton, the hypothetical carrier of gravity. In theories with large extra dimensions, this graviton could, right after its creation, simply drift off our three-dimensional brane and into the bulk. From our perspective, it would vanish. It would carry away a portion of the collision's energy and momentum, leaving no trace in the detectors. The ledger would not balance. This is the signature physicists hunt for: missing energy, a collision event where the detected particles simply do not add up, pointing to something invisible carrying away the difference. Finding such an event would be a monumental discovery, a direct fingerprint of something escaping our dimensional prison. The challenge is staggering. The Large Hadron Collider produces over 1 billion collisions per second. Sifting through this ocean of data for a handful of anomalous events is like searching for a single, unique grain of sand on all the beaches of the world. Teams of researchers design sophisticated algorithms to filter the data, looking for the specific patterns that missing energy would create. While no definitive signal has yet emerged, the very absence of evidence is itself a powerful result. Each analysis that comes up empty further constrains the possibilities. It tells us that if extra dimensions exist, they must be smaller than a certain scale, or that their properties must be configured in ways that make this particular escape more difficult. In this way, the collider acts as the most powerful microscope ever built, not by magnifying with lenses, but by probing with sheer energy. It is systematically scanning the finest scales of reality, shaking the foundations of space and listening intently for a tremor that suggests there is more to the structure than we can see. While particle accelerators probe the violent present, our oldest and quietest light holds echoes of a more dramatic era. The cosmic microwave background is a whisper from the very beginning, a snapshot of the universe when it was a mere 380,000 years old. This faint glow, mapped in exquisite detail by observatories like the Planck satellite, is not a uniform blanket. It is a tapestry of minute temperature variations, a pattern of slightly warmer and cooler spots frozen in time. Cosmologists read this pattern like a cosmic fingerprint, searching for clues about the universe's explosive birth and its fundamental structure. If extra dimensions existed in that primordial furnace, their influence would have been profound, potentially leaving a subtle signature in this ancient light. In the first fractions of a second after the Big Bang, all of space was compressed to an unimaginably hot, dense state. This was a realm of extreme energy where the distinctions between forces blurred and the geometry of reality itself may have been fluid and dynamic. Hidden dimensions, if they are part of that geometry, would not have been curled and frozen as they are today. They could have been expansive and active, influencing how the infant universe inflated and cooled. One tantalizing possibility involves the primordial gravitational waves generated by that initial cataclysm. These are not the ripples from colliding black holes we detect today, but vastly older undulations in spacetime itself, stretching from the universe's first tremors. The presence of extra dimensions in the early cosmos could have altered how these waves were generated and how they propagated, affecting their spectrum, the range of their frequencies and strengths. While we have not yet detected these specific ancient waves, Their predicted imprint could subtly change the polarization pattern of the cosmic microwave background, a specific swirled signature in the light that future telescopes are designed to hunt with incredible precision. Furthermore, the pattern of hot and cold spots in the background radiation and the vast web of galaxies that later formed from those seeds carries statistical information about the initial conditions of the cosmos. Certain anomalies or preferred alignments in this large-scale structure, patterns that are difficult to explain with standard three-dimensional inflation, could be hints of a more complex, higher-dimensional origin story. It is a form of cosmic archaeology. We are not digging in the ground, but sifting through the statistical properties of the oldest light and the distribution of matter across billions of light years. Each precise measurement is a brushstroke helping us reconstruct the hidden geometry of the universe's first moments. By connecting the colossal scales of the cosmic web to the infinitesimal realm of fundamental physics, cosmologists are performing a breathtaking act of deduction. They are using the universe itself as the ultimate laboratory, searching for the architectural fingerprints of dimensions we may never directly see, imprinted forever in the sky. That staggering difference in strength is not just a curiosity, it is a crisis for our understanding. 1 followed by 36 zeros is a number so large it defies everyday analogy. If the electromagnetic force were the height of Mount Everest, gravity's relative strength would be less than the thickness of a single sheet of paper. This extreme imbalance is known as the hierarchy problem, and it points to a deep unease in physics. Why should nature's forces be so wildly out of balance? In our standard models, this weakness of gravity is not explained. It is simply a number we must plug into the equations by hand, an arbitrary, fine-tuned input that makes the universe work. To many theorists, this feels profoundly unnatural, like finding a perfectly balanced pencil standing on its tip for billions of years. There must be a reason, a structural cause that makes this immense gap not a coincidence, but a consequence of a deeper reality. This is where the geometry of hidden dimensions offers a breathtakingly elegant solution. In the Brane world model proposed by Lisa Randall and Raman Sundaram, gravity is not inherently weak. Its fundamental strength, they propose, is actually on par with the other forces. The staggering difference we measure is an illusion of our perspective. Imagine you are living on the surface of a vast, calm lake. A powerful storm is raging in the sky above, but you cannot feel the full force of the wind because you are sheltered on the water's surface. You only experience the ripples and disturbances that make it down to your level. In their model, our three-dimensional universe is a membrane floating within a higher dimensional space that is not flat but dramatically warped. This warping acts like a gravitational well, a steep slope in the geometry of the extra dimension. Our brain, where all known particles and forces except gravity are trapped, sits at one end of this warped throat. The true source of gravity's strength resides far away, on a different brane or deep within this warped geometry. By the time its influence reaches us, it has been exponentially diluted by the warped space it had to traverse. Gravity appears fantastically weak to us because we are seeing only the faint, diluted echo of its full power. This is not a small adjustment, it is a complete reframing. The hierarchy problem vanishes because there is no longer a fundamental imbalance to explain. The forces are all strong at their source, but we experience them differently based on where we are stuck in the cosmic geography. One is local to our brain, the other is filtered through a hidden, warped dimension. This transforms the search for extra dimensions from a speculative quest into a direct assault on one of physics' most nagging mysteries. Finding evidence for large extra dimensions would not just add new rooms to reality's house, it would solve the architectural puzzle of why the foundation feels so strangely lopsided. It would tell us that the universe's parameters are not random, accidental numbers, but the natural, inevitable outcome of a hidden geometric truth. the vacuum of space is not truly empty. According to quantum physics, it is a seething, bubbling sea of virtual particles flickering in and out of existence, each pair contributing a tiny bit of energy. When physicists calculate the total energy density of this quantum vacuum, the number they get is monstrous. It should be 1 followed by 120 zeros larger than the energy density we actually observe driving the universe's expansion. This is the cosmological constant problem, and it represents the worst theoretical prediction in the history of science. If the quantum calculation were correct, the universe would have torn itself apart in a violent explosion moments after the Big Bang, or collapsed back in on itself instantly. The fact that we exist, that galaxies formed, tells us this number must be almost perfectly cancelled out, leaving only a whisper of positive energy behind. But why? How does nature achieve this unimaginable fine-tuning? The geometry of hidden dimensions might hold the key. In theories where our universe is a brane, the gravitational pull of other, parallel branes in the bulk, or the specific way our brane is curved and stretched, could create counterbalancing forces. These forces from the higher dimensional geometry might precisely offset the huge quantum vacuum energy we calculate, leaving only the tiny residual we measure as dark energy. It's a cosmic balancing act on a knife's edge, mediated by the unseen architecture around us. String theory offers another, more sweeping possibility through its vast landscape of possible Calabi-Yau shapes. Each distinct geometry yields a different vacuum energy, a different value for that cosmological constant. In an unimaginably vast multiverse, every possible number is realized somewhere. Universes with large positive energy blow apart too fast for stars to form. Those with large negative energy recollapse instantly. Only in the extraordinarily rare patches where the numbers almost miraculously cancel, leaving a tiny positive value, can galaxies, planets, and curious minds emerge to ponder the question. This is the anthropic principle in its starkest form. We do not observe a finely tuned universe because it was designed for us. We observe it because we are the products of that specific, rare tuning. Our search for the reason behind the numbers leads us back to the hidden dimensions. Their specific, frozen geometry may not just dictate particle masses, but may have also locked in the faint, repulsive energy that is now gently pushing the cosmos apart. This transforms the quest from a search for hidden forces into a search for the reason we are here at all, and what the ultimate fate of our expanding home will be. But the search for hidden geometry reaches beyond the forces and into the very substance of the cosmos. For nearly a century, astronomers have known that something is missing. Galaxies spin too fast, and clusters of galaxies hold together with a gravitational grip far stronger than the visible stars and gas can provide. The universe is held together by a ghost, a substance that does not shine, reflect, or absorb light in any way we can detect. We call it dark matter, and it constitutes roughly 85% of all the matter in existence. We feel its gravitational pull sculpting the cosmos, but we have never seen its face. Could this profound enigma be our next clue in the search for hidden dimensions? Could dark matter not be a new type of particle in our three-dimensional world, but something that lives in or interacts with the extra realms we have been exploring? Some of the most compelling theories suggest exactly that. In the brane world picture, where our universe is a membrane floating in a higher dimensional bulk, a startling possibility emerges. The dark matter that dominates our galaxy might be perfectly ordinary matter, but from a parallel brane hovering incredibly close to our own in the hidden direction. Think of two sheets of paper suspended a microscopic distance apart. The atoms on our sheet cannot reach over to the other, but their gravity, leaking into the bulk, can. From our perspective, the stars and planets on that neighboring brane would be completely invisible, yet their collective mass would tug on our stars and galaxies, providing the exact gravitational scaffolding we observe. They would be right here, yet in a place we cannot touch. This elegant idea transforms dark matter from an exotic particle into a cosmic neighbor, separated by a gap we cannot cross. An alternative, equally fascinating idea comes directly from the legacy of Kaluza-Klein. If extra dimensions are curled up, then particles moving through them would have momentum in those hidden directions. From our three-dimensional viewpoint, this extra momentum would manifest as additional mass. These are called Kaluza-Klein particles, and they are essentially vibrational echoes of ordinary particles ringing in the compactified dimensions. The lightest and most stable of these echoes could be the perfect dark matter candidate. It would interact with our world almost exclusively through gravity, just as the cosmic evidence demands, and it would have a specific, calculable mass range determined by the size and shape of the hidden dimensions. This gives physicists a tangible target. Experiments deep underground, designed to catch the incredibly rare bump of a dark matter particle, are now tuned to search for these specific Kaluza-Klein signatures. The search for the missing mass of the universe thus converges with the search for hidden architecture. Finding a particle that is a whisper from a curled-up dimension would solve two of physics' greatest puzzles at once. It would reveal the nature of the cosmic ghost and, in the same moment, hand us a map to the unseen folds of reality. The dark that fills the spaces between the stars may not be empty at all, but crowded with the geometry of everything we have yet to see. Yet the most extreme test of hidden dimensions may not be forged in our machines, but in nature's own crucibles of gravity. Black holes are the ultimate laboratories for such a test. These regions of space-time where gravity becomes so overwhelming that not even light can escape are not just cosmic curiosities. They are pure expressions of geometric law where the fabric of reality is tied into a knot. In a universe with extra dimensions, the very nature of these knots would be rewritten. The way a black hole forms, its temperature, and even how it might eventually evaporate, all depend intimately on the number of dimensions gravity can spread into. This leads to a startling possibility. If extra dimensions are large enough, the energy needed to create a microscopic black hole could drop dramatically. In our familiar three-dimensional world, creating a black hole requires compressing a star's worth of mass into a tiny volume. But if gravity operates in more dimensions, its strength increases at short ranges, making it easier to warp spacetime into that ultimate curve. This means that in the furious collisions of a particle collider like the Large Hadron Collider, for a fleeting instant, the conditions might just be right to stitch a micro-black hole into existence. It would be a speck smaller than a proton, a gravitational whirlpool in the higher dimensional bulk, and according to Stephen Hawking's revolutionary work, such a tiny black hole would not be eternal. It would evaporate in a flash, decaying through a process called Hawking radiation, producing a distinctive, energetic shower of particles in the detector. While no such signal has been found, its discovery would be an unequivocal revolution. It would be a direct creation and dissection of a higher dimensional object, a tiny tear in the familiar fabric of space revealing the fuller geometry beneath. But we need not create black holes to learn from them. The universe makes them on a colossal scale. When two black holes spiral together and merge, they shake the fabric of spacetime, sending out ripples called gravitational waves. Observatories like LIGO and Virgo have begun to catch these faint whispers from these cosmic catastrophes. Each wave's shape is a detailed fingerprint of the event that created it, encoding the masses and spins of the black holes. Crucially, it also encodes the properties of the spacetime they traveled through. If that spacetime has hidden dimensions, the waves could carry subtle imprints of that fact. The ringing of the newly formed black hole, the specific frequencies at which it settles down, could be slightly altered. It is an extraordinarily delicate measurement, like listening to a bell ring in a cathedral and deducing the shape of a hidden room by a barely perceptible echo in its tone. Turning these signals from the most violent events in the cosmos into precision tests for hidden realms is the frontier of gravitational wave astronomy. Each new collision we detect is another chance to listen for the hidden architecture of reality, written in the silent language of rippling gravity. This search pushes against the very limits of how our minds are built. Our brains evolved to navigate a world of length, width, and height, to judge distances, to grasp objects, and to avoid predators on a three-dimensional landscape. This wiring is so fundamental that trying to genuinely visualize a fourth spatial dimension is, for most of us, a cognitive impossibility. We can talk about it, we can write equations for it, but we cannot truly see it in our mind's eye. This is the profound challenge of visualization, and it forces us to confront a humbling possibility. What if our entire perceived reality is not the full picture, but merely a projection? Think of the shadow cast by a twisting, turning hand. On a flat wall, that shadow is a two-dimensional silhouette, a simplified and distorted representation of the complex three-dimensional object creating it. The shadow cannot convey the hand's depth, the spaces between the fingers, or the roundness of the palm. It only shows a flattened outline. Now extend that analogy upward. What if our three-dimensional universe, with all its richness of form and force, is itself a kind of shadow, a three-dimensional projection or membrane cast by processes and objects existing in a higher dimensional reality? We are, in a sense, the flatlanders of a grander cosmos, confidently interpreting the shadows on our cave wall, while the true actors move unseen in the light. To even hint at these hidden structures, mathematicians and artists rely on clever analogies and tools of inference. One powerful method is the use of projections. Just as a globe can be projected onto a flat map, a four-dimensional object, like a hypercube or tesseract, can be projected into three dimensions. The resulting model looks like a cube within a cube, with all their corners connected by lines. It is a strange, collapsing shape that seems to pass through itself. This model is not the hypercube itself, but its three-dimensional shadow, a ghostly imprint that hints at properties we cannot fully render. Another tool is the cross-section. Imagine slicing a three-dimensional apple with a knife. The revealed surface is a two-dimensional shape, a circle that changes as you move the slice. In the same way, if a four-dimensional object were to pass through our three-dimensional space, we would not see the whole object at once. We would see a three-dimensional cross-section that would morph and change in seemingly impossible ways, like a sphere that appears, grows, shrinks, and vanishes without ever moving in a familiar direction. These exercises are not about achieving a perfect mental picture. They are about training our intuition to accept that the true nature of these dimensions may forever lie beyond our direct sensory imagination. The search, therefore, shifts from a visual hunt to a forensic one. We are not looking for something we can picture in a conventional sense. We are searching for mathematical consistency, for the elegant equations that only balance when given more room, and for the subtle, experimental fingerprints these unseen geometries leave on our world. The language of this deeper reality may not be one of images, but of mathematics and measurement, a code we are learning to decipher in the quiet data of colliders and the ancient patterns of the sky. These ideas push beyond the equations and into the very foundations of how we understand our place in the cosmos. Our relentless search for hidden dimensions carries a profound, almost unsettling philosophical weight. It forces a simple yet deeply challenging question. If the true nature of reality is structured in ways our biology permanently prevents us from directly experiencing, then what can we ever truly claim to know? We are like the individuals in an ancient story who spent their entire lives chained in a cave, seeing only the flickering shadows cast on a wall by a fire behind them. For them, those shadows were the sum total of reality. They had no framework, no language, even to conceive of the three-dimensional objects casting those shapes, let alone the world outside the cave. Are we confidently measuring our three-dimensional universe in a similar predicament? Could the particles, forces, and laws we meticulously catalogue be mere shadows, flat projections of objects and interactions playing out in a realm of higher geometry? This is not a dismissal of science, but a humbling acknowledgement of its context. Every tool we build, from microscopes to particle colliders, is an extension of our senses, designed to probe deeper into the cave wall. They give us sharper, more detailed views of the shadows, but they do not, by themselves, grant us the ability to turn our heads and see the light source. Our knowledge becomes a brilliant, self-consistent map of the cave wall, while the true territory remains inferred, deduced through the elegance of mathematics and the persistence of unexplained clues. This leads us directly to the anthropic principle, a logical mirror held up to our investigation. It observes that we, as conscious observers made of complex chemistry, can only exist in a universe with very specific conditions. The constants of nature in our three-dimensional slice appear finely tuned to allow for atoms, stars, planets, and life. But is this tuning a miraculous coincidence or a selection effect? If the landscape of possible universes, or the possible ways dimensions can compactify, is vast beyond imagining, then of course we find ourselves in one of the rare, stable pockets where the numbers work out. We do not observe a universe with 10 expansive dimensions because complex structures like us could not form there. Our perception is limited to the slice of reality that can produce perceivers. In this view, our three-dimensional experience is not the grand, central stage of existence. It is a quiet, habitable backwater in a much wilder, more expansive cosmic archipelago. The search for hidden dimensions, then, becomes a search for the shoreline, for evidence of the greater ocean that surrounds our island of perception. Ultimately, this journey challenges the most basic definition of what we consider real. We trust our senses to report an objective world, but they evolved for survival on a planetary surface, not for mapping the geometry of the cosmos. Reality, in the fullest sense, may be something that is fundamentally unseeable in its entirety. The solidity of a table, the orbit of a moon, the heat of a star, these could be persistent, reliable interactions within our dimensional slice, yet still be partial expressions of a deeper truth. This does not make our world an illusion. The shadows in the cave are real shadows. The laws of physics we discover are real laws, governing our layer of existence with magnificent precision. But they may be local bylaws, not the ultimate constitution. The promise and the profound challenge of this search is the possibility that through the indirect language of mathematics and experiment, we might one day read the shape of that constitution. We are creatures of a three-dimensional cave, but we have learned to measure the shadows with such exquisite care that we can begin to sketch the outlines of the objects casting them, dreaming of a light whose source we may never directly behold, yet whose existence would forever change our understanding of what it means to be here. The quest for hidden dimensions is a story of pure curiosity, a search for answers to questions that may have no immediate application. Yet history reveals a profound truth about this kind of exploration. When we stretch our minds to the absolute limits of the possible, we do not just gain new knowledge, we are forced to invent entirely new ways of seeing, measuring, and calculating. This relentless drive to probe the unseen fabric of reality has, time and again, spun off technologies that reshape our everyday world in unforeseen ways. Consider the search for those minute deviations in gravity's strength at microscopic distances. To measure a force 1 billion times weaker than the weight of a snowflake, scientists cannot use ordinary tools. They must pioneer them. This challenge has led to breakthroughs in creating materials of incredible stability, sensors of almost magical sensitivity, and systems of vibration isolation so effective they can quiet the tremors of a bustling city or even the ocean's waves. The techniques developed to shield a delicate experiment from a passing truck are now finding uses in improving the precision of medical imaging devices, making microchip manufacturing more reliable, and creating navigation systems of unprecedented accuracy. The abstract goal of testing gravity's law has quietly advanced the entire science of measurement, giving us finer control over the physical world. Then there is the computational frontier. Simulating the complex geometries of Calabi-Yau manifolds or modeling the collisions in a string theory landscape is a task of staggering complexity. It requires not just raw computing power, but entirely new algorithms to handle multidimensional mathematics. The push to visualize these hidden shapes has driven innovation in supercomputing and data analysis, contributing to the same toolkit used for climate modeling, pharmaceutical drug discovery, and unraveling the folds of proteins in our own bodies. The software written to chart a six-dimensional universe can help us understand the intricate three-dimensional machinery of life. Even our gaze upward is sharpened by this search. The hunt for subtle imprints of extra dimensions in the cosmic microwave background demands telescopes and detectors of phenomenal sensitivity and resolution. The technology developed to pass the faintest whispers from the dawn of time directly improves our satellite communication networks, enhances Earth observation for agriculture and environmental monitoring, and refines the detectors used in security and medical scanning. Perhaps most intriguing are the conceptual spin-offs. The very idea of information being encoded in the geometry of hidden dimensions, or of reality having a holographic nature where a lower dimensional surface holds all the data of a higher dimensional volume, has inspired fresh thinking in computer science and cryptography. Researchers explore how to store and protect information in new ways, drawing metaphors from the physics of branes and bulk. The study of complex, emergent systems in theoretical physics informs how we analyze financial markets, traffic patterns, and the spread of ideas through a society. This is the beautiful, recurring dividend of fundamental science. We set out to map the shores of the unknown, driven by wonder alone. To make the journey, we must learn to build better ships, craft finer instruments, and draw more detailed charts. Those tools, forged in the fire of pure inquiry, inevitably find their way back to harbor, improving the lives of everyone. The search for hidden dimensions is more than a philosophical adventure. It is a quiet, powerful engine for human ingenuity, proving that the act of looking deeply into the cosmos forever changes how we live upon our own world. Yet for all its elegant promise, this grand search for hidden dimensions is not a settled story. It is a frontier, and like any frontier, it is marked by vigorous debate and profound skepticism. Some of the most respected voices in physics raise a critical question. If these dimensions are so hidden, so curled up at scales beyond our direct reach, can we ever truly test for them? This touches on a foundational principle of science itself, championed by the philosopher Karl Popper. For an idea to be scientific, it must be falsifiable. That is, there must be a conceivable experiment or observation that could prove it wrong. Critics argue that many formulations of string theory and its extra dimensions have drifted into a realm of mathematical metaphysics, beautiful and internally consistent, but seemingly insulated from experimental challenge. If a theory can accommodate any possible outcome by adjusting its hidden parameters, they ask, does it actually tell us anything about the real world? This concern is sharpened by what is known as the landscape problem. The mathematics of string theory does not point to one unique universe, but to a staggering multitude of possible configurations, perhaps 10 to the 500 or more. Each represents a different way the extra dimensions could be folded, each yielding a different set of physical laws and constants. With such an immense landscape of possibilities, almost any observed value in our universe could be explained by simply saying we live in one particular patch where the numbers work out this way. For some scientists, this feels less like a precise prediction and more like a retreat from prediction. If the theory can describe nearly everything, they argue, it risks explaining nothing specific at all. These criticisms have spurred the development of alternative paths toward unifying gravity and quantum mechanics, roads that do not travel through hidden dimensions. One prominent route is loop quantum gravity. Instead of adding extra dimensions or tiny strings, this approach seeks to rewrite the geometry of spacetime itself at the smallest scales. It proposes that space is not a smooth continuum, but is woven from tiny, discrete loops, a fabric of finite threads. In this view, the familiar three dimensions of space emerge from a more fundamental, granular network of connections. There are no extra dimensions to hide, but a radical new picture of the dimensions we already have. Another approach, causal set theory, suggests that reality at its core is just a collection of discrete events with a defined order of cause and effect. The smooth flow of time and the expanse of space we experience are large-scale approximations of this underlying pointillist structure. These frameworks represent a very different philosophical stance, building reality from the bottom up from quantum principles, rather than from the top down from elegant, higher-dimensional geometry. Acknowledging this vibrant debate is not a sign of weakness in the search, but a testament to its vitality. This is how science progresses at its cutting edge, through a fierce and necessary dialogue between imagination and evidence, between elegant theory and stubborn reality. The quest for hidden dimensions is not a dogma to be accepted, but a magnificent hypothesis to be tested. Its ultimate validation, or its graceful retirement, will not come from mathematical beauty alone, but from a single, reproducible fingerprint in the data, a whisper from the cosmos that says, "Look closer, there is more here than you can see." The journey continues not in certainty, but in a state of profound and productive curiosity, where every criticism sharpens the question and every alternative path reminds us that the truth, whatever it may be, has no obligation to conform to our aesthetic preferences. The universe will reveal its structure in its own way, and our task is to learn how to listen. The language of the cosmos is written in numbers and shapes. For centuries, physicists have marveled at what Eugene Wigner called the unreasonable effectiveness of mathematics. The abstract rules of geometry and algebra, creations of the human mind, turn out to describe the orbits of planets, the flow of electricity, and the dance of subatomic particles with breathtaking precision. This uncanny alignment forces a deep philosophical question. Are we inventing these mathematical structures, or are we discovering them? When a mathematician like Bernhard Riemann devised a system for describing curved spaces of any dimension, was that a free act of imagination, or was it uncovering a truth that existed independently, waiting to be found? The search for hidden dimensions sits at the very heart of this mystery. The work of Kaluza-Klein and later the string theorists did not begin with a startling observation from a telescope or a particle detector. It began with pencil on paper, with the pursuit of mathematical beauty and internal consistency. They followed the equations where they led, even when that path pointed to realities that seemed, at the time, purely abstract and beyond any hope of experimental test. The extra dimensions first emerged not as a physical hypothesis, but as a mathematical necessity for the equations to make sense. This pattern suggests something remarkable. Mathematics is not merely a tool we use to describe the world after we see it. It can act as a divining rod, a guide pointing toward features of reality we have not yet learned to perceive. The physicist trusts that nature herself is written in this elegant, logical language. The complex geometries of Calabi-Yau manifolds or the warped throats of Brane worlds are not whimsical fiction. They are detailed maps drawn from first principles, maps of territories we are only now building the instruments to explore. This interplay blurs the line between discovery and creation. Did we invent the concept of a 10-dimensional universe, or did the universe, in its fundamental structure, always contain those dimensions, and we are slowly, painstakingly discovering the vocabulary to speak of them? The process feels less like building a model from scratch and more like translating a text from a foreign tongue. We work with the symbols we have, the mathematics, and we strive to arrange them into a coherent narrative. When the pieces click together with a satisfying elegance, when a single equation like Kaluza's can generate two fundamental forces, it feels like we have stumbled upon a clause in the cosmic constitution. This raises a profound and humbling possibility about the connection between our minds and the universe. Why should the deep, abstract patterns woven by human thought resonate so perfectly with the deep, physical architecture of reality? Is it because our logic is a product of a logical universe, our minds evolved within its rules and therefore tuned to comprehend them? Or does it point to something even more fundamental, a shared grounding in a realm of perfect forms and relations? The search for hidden dimensions, then, is more than a scientific endeavor. It is a test of this deep-seated faith in a rational, mathematically eloquent cosmos. Every time we build a machine to hunt for a graviton leaking into the bulk, or analyze starlight for a signature of compactified geometry, we are not just testing a theory of physics. We are testing a philosophy. We are asking the universe if our most beautiful and consistent stories about it are, in fact, true stories. The answer, whatever it may be, will tell us not only about the shape of space, but about the very nature of knowledge and our place within a reality we strive to understand. The next chapter of this search will be written not just on paper, but in space itself. A new generation of experiments, more precise and ambitious than ever before, is poised to turn our theoretical questions into measurable data. Leading this charge is a mission that will listen to the universe in a way we never have. The Laser Interferometer Space Antenna, or LISA, is a planned constellation of 3 spacecraft flying in a vast triangle millions of kilometers apart. By monitoring the distance between them with laser beams of phenomenal accuracy, LISA will detect the low-frequency rumble of gravitational waves that ground-based observatories cannot hear. This will open a new window onto the cosmos, one where we might hear the faint, persistent hum of cosmic strings, hypothetical relics from the universe's earliest moments that could be direct evidence of a phase transition involving higher dimensional physics. It could also catch the distant chorus of millions of merging supermassive black holes, and in their unique gravitational waveforms, scientists will search for the subtle distortions that would betray the presence of extra dimensions warping spacetime on a galactic scale. Back on Earth, the frontier of the vanishingly small is also being pushed with astonishing ingenuity. Tabletop experiments are becoming laboratories of extreme precision. Some will use clouds of atoms cooled to near absolute zero, suspended in vacuum chambers by lasers, to act as exquisitely sensitive probes for minuscule forces. Others will employ nanomechanical devices, tiny vibrating bars or membranes, to feel for any deviation in gravity's pull at distances smaller than the width of a human hair. These are not colossal machines, but marvels of miniaturization, designed to hunt for the telltale strengthening of gravity that would signal a large extra dimension just a fraction of a millimeter away. They represent a quiet, relentless effort to scan the finest scales of our reality, meter by meter, for a door we cannot see. Meanwhile, the quest for higher energy continues. Proposals for a future circular collider, a successor to the Large Hadron Collider with a circumference potentially 4 times larger, aim to smash particles together with unprecedented force. The goal is to reach energies that could, if the dimensions are right, produce not just hints but undeniable signatures. This could mean creating a shower of particles with the specific energy patterns of Kaluza-Klein excitations, or even, in the most dramatic scenario, the brief, fiery birth and evaporation of a microscopic black hole. Each collision in such a machine would be a recreation of the universe's most primal energies, shaking the fabric of space-time with enough violence to make the hidden geometry ring. Beyond pure force, another approach watches for change over immense time. Atomic clocks, already the most precise timekeeping devices ever built, are becoming so stable that they can detect variations in fundamental constants over years or decades. If the size or shape of hidden dimensions is not perfectly static but subtly dynamic, it could cause infinitesimal shifts in the strength of forces or the masses of particles over cosmological time. Monitoring these constants with networks of clocks on Earth and in space is like taking the universe's vital signs across centuries, watching for a slow, steady heartbeat that indicates a living, breathing geometry beneath our own. This expanding experimental frontier transforms the search from a theoretical hope into a tangible, multi-pronged investigation. We are building ears to listen to the low notes of the cosmos, fingers to feel the texture of space at its finest grain, furnaces to recreate primordial fire, and clocks to measure the age of the universe with patience. Each approach offers a new path to the same destination, a new method for asking reality if there is more to the story. The coming decades promise not just more data, but a symphony of it, and somewhere in that harmony, we hope to find the first clear note of a higher dimensional truth. The mathematics of hidden dimensions opens a door to a possibility far grander than a single unseen realm. It suggests our entire cosmos may be just one page in an infinite library. This is the multiverse hypothesis, and it emerges not as a separate idea, but as a direct, almost inevitable consequence of the geometry we have been exploring. Within the framework of string theory, there is not one unique way to curl up the extra 6 or 7 dimensions. The number of mathematically consistent configurations for these Calabi-Yau shapes is staggering, perhaps as many as 10 to the power of 500. Each distinct fold, each specific geometry, defines a different set of physical laws. One particular curl of the hidden dimensions might yield a universe where the strong nuclear force is slightly stronger, preventing atoms from ever forming. Another might produce a cosmos where electromagnetism is too weak for chemistry and stars never ignite. Our universe, with its 3 expansive dimensions, its specific particle masses, and its life-permitting constants, represents just one possible outcome, one specific valley in an unimaginably vast landscape of potential realities. We are not living in the only possible universe. We are living in one that is possible for us. This landscape picture transforms the search for a single theory of everything into a cosmic census. The fundamental question shifts from why our laws are what they are to why we find ourselves in this particular corner of the landscape. The answer may be unsettlingly simple. Universes with different physical parameters might be stillborn, collapsing instantly or expanding so rapidly that no complex structures ever arise. Only in the rare pockets where the numbers align with exquisite precision can galaxies, planets, and conscious observers emerge to ponder the question. Our existence becomes a selection effect, a filter through which we only perceive the universes capable of producing perceivers. This idea, known as the anthropic principle, is not an explanation in the traditional sense, but a logical framework for understanding our place in a potentially infinite ensemble. It suggests the fine-tuning we marvel at is not a miracle, but a necessity for our own presence. The multiverse concept naturally extends to the very structure of space itself. If our 3 large dimensions are the result of how our particular cosmic bubble inflated, could other bubbles in this frothing multiverse have stabilized with a different number of expansive dimensions? Absolutely. One universe might have 2 large spatial dimensions, a flatland on a cosmic scale. Another might have 4, 5, or more dimensions we would perceive as vast and navigable. The beings in those realms would experience a physics utterly alien to our own, built upon a geometry we can describe mathematically but could never truly visualize. Their reality would be as natural to them as ours is to us, each a valid expression of the underlying mathematical possibilities. This speculative leap shows how the search for hidden dimensions in our own backyard is merely the first step. It acts as a gateway, leading us to consider the totality of existence, a realm where every mathematically consistent universe might somewhere be real. Yet this breathtaking vision brings with it profound challenges, especially for the scientific method. If the multiverse is real and nearly all possible laws are realized somewhere, how can we ever make a specific, testable prediction? Any observation we make in our universe could be explained by saying we simply occupy the bubble where that observation holds true. This threatens to move the discussion from the realm of testable physics into the domain of metaphysics, where elegance and possibility replace falsifiable prediction. For many scientists, this is a serious concern, a potential retreat from the hard-won principle that a theory must stake its claim on what we should not see. The multiverse hypothesis, born from the elegant mathematics of hidden dimensions, now stands at this difficult frontier. It pushes us to ask what science can truly say about realities forever beyond our causal horizon, and whether the ultimate nature of existence might always retain an element of profound, untestable mystery. The profound mystery of hidden dimensions does more than challenge physicists, it captivates the public imagination. This very difficulty in visualizing higher realms becomes a powerful gateway for inspiring the next generation of scientists, engineers, and curious minds. Science communicators face the unique task of translating abstract mathematics into stories we can feel, using tools that spark wonder rather than confusion. They turn to vivid analogies, comparing curled-up dimensions to the unseen thickness of a garden hose or our universe to a shadow cast by a higher dimensional object. Interactive simulations allow anyone to manipulate virtual Calabi-Yau manifolds, watching how changing a hidden shape could alter the laws of physics in a simulated universe. Artists collaborate with theorists to create stunning visualizations, giving form to equations and painting the unseen geometry that might underpin reality. These creative efforts bring the frontier of theoretical physics out of academic journals and into the light of shared experience. Planetarium shows transport audiences through warped space-time. Popular science books turn complex concepts into narrative journeys, and online creators build communities where enthusiasts can debate Brane worlds and multiverses. This outreach does more than disseminate information. It teaches a deeper lesson about the scientific process itself. The decades-long search for extra dimensions is a masterclass in grappling with the unknown. It showcases the essential role of disciplined imagination, where beautiful mathematics guides the way, and the patient, collective accumulation of knowledge, where each null result from a delicate experiment or particle collider narrows the path forward. By sharing this ongoing, unfinished quest with honesty and enthusiasm, we do more than explain a theory. We model a mindset. We encourage critical thinking, resilience in the face of profound mystery, and above all, a sense of wonder about our place in the cosmos. The student who is captivated by a video about gravity leaking into the bulk, or the amateur astronomer who ponders the imprint of extra dimensions in the cosmic microwave background, might just be the one who, in a few decades, designs the ingenious experiment that finally reveals the hidden layers of our reality. This shared journey of curiosity ensures the search continues, powered by every new mind that looks at the night sky and asks, what are we not seeing? Our struggle to see beyond 3 dimensions is not just a puzzle for physicists. It is a fundamental human challenge that echoes across disciplines. Artists have long wrestled with the limits of a flat canvas, seeking ways to suggest more than the eye can see. In the early 20th century, the Cubist movement, led by figures like Pablo Picasso and Georges Braque, shattered the single-perspective tradition of Western art. They painted objects from multiple angles at once, fracturing a guitar or a face into geometric planes that suggested a fuller reality captured in a single moment. This was not a literal depiction of a fourth dimension, but a profound artistic rebellion against a fixed viewpoint. It was an intuitive leap toward representing a more complex truth, a metaphorical acknowledgement that what we perceive is always a limited slice of a richer whole. This artistic impulse to transcend our perceptual limits finds powerful expression in narrative too. Edwin Abbott's 1884 novella Flatland remains the seminal exploration, using a two-dimensional world to satirize Victorian society while making the concept of higher dimensions hauntingly tangible. More recently, films like Interstellar visualize higher dimensional spaces as tangible, navigable realms where time becomes a physical landscape. These stories are not mere science fiction spectacles. They are thought experiments that ask us to empathize with beings of different dimensional experience, forcing us to confront the fragility of our own perceived reality. This exploration moves from the external world to the internal machinery of our own minds. Neuroscience reveals that our confident experience of a three-dimensional world is itself a magnificent construction. Our eyes provide only two-dimensional projections on the retinas, flat images like two slightly different camera feeds. The brain performs an extraordinary feat of computation, stitching these inputs together, using shadows, motion parallax, and prior experience to build a seamless, immersive model of volumetric space. We do not see in three dimensions, we infer in three dimensions. Our perception is a best-guess simulation, a user interface generated by the brain to help us navigate successfully. In a very real sense, we are already living inside a processed reality, a lower dimensional representation built from even lower dimensional data. This raises a provocative parallel. The brain's model building is not unlike a physicist's mathematical modeling of a higher dimensional bulk from which our familiar forces emerge. Both are acts of reverse engineering a deeper structure from limited sensory or experimental data. Even our handling of information in the digital age draws on these geometric intuitions. In data science, techniques known as manifold learning tackle a very practical problem. Imagine you have a vast dataset with thousands of measurements per item, like detailed genetic profiles or high-resolution images. This data exists mathematically in a space of thousands of dimensions, a realm impossible to visualize. Yet, the meaningful patterns within it, the true structure, often lie on a much lower dimensional surface curled and folded within that high-dimensional void. Algorithms work to unfold this hidden manifold, much like flattening a crumpled sheet of paper, to reveal the essential 2 or 3 dimensions that capture the data's core relationships. This process is a direct application of the geometric principles from our physical theories, used to find simplicity and pattern within apparent chaos. From the artist's canvas to the brain's visual cortex to the statistician's algorithm, the same theme recurs. We are pattern-seeking creatures constantly building models of the world, and the concept of hidden dimensions provides a powerful framework for this endeavor. It is a metaphor, a mathematical tool, and a physical hypothesis all at once, revealing that the quest to map the universe's unseen geometry is ultimately part of the timeless human project to understand the very nature of structure, perception, and the profound limits of our own point of view. The scale of this hidden geometry is almost beyond human comprehension. The most elegant versions of string theory suggest the extra dimensions are curled up at a size known as the Planck length, a distance of 10 to the power of -35 meters. To grasp that number, consider the size of a single atom. Now shrink that atom down to a scale as much smaller than itself as it is smaller than our entire solar system. You are still not close. At this scale, space and time themselves may lose their smooth continuity, becoming a frothing quantum foam. This is the realm where the hidden dimensions are theorized to be compactified, a billion times smaller than the tiniest distances we can currently probe with our most powerful tool, the Large Hadron Collider. To directly observe physics at the Planck scale by brute force, by smashing particles together with enough energy to illuminate it, we would need a machine of unimaginable proportions. Theoretical estimates suggest a collider would need to be roughly the size of our entire galaxy, harnessing energies that dwarf anything our civilization could ever conceive of producing. This is not a limitation of funding or will, but a fundamental barrier written into the laws of physics and engineering. We simply cannot build our way to that direct view. This immense gap forces a profound shift in strategy. Physicists cannot aim a microscope at these dimensions. Instead, they must become cosmic detectives, searching for indirect clues, subtle fingerprints left in the wider universe. They look for minute imperfections in the cosmic microwave background that might be echoes of that compactified geometry. They design tabletop experiments of breathtaking sensitivity to feel for the faintest deviation in gravity's pull at microscopic distances. They scour data from particle colliders not for the dimensions themselves, but for missing energy or exotic particles that could only exist if those dimensions are there. Acknowledging these limits is not an admission of defeat, it is the honest definition of a frontier. It reveals that this search is a long-term, generational endeavor. The solution may not come from a single, monumental experiment, but from a slow accumulation of puzzling clues from many different fields, pieced together over decades. It may require a leap in theoretical insight as profound as relativity or quantum mechanics, a new way of thinking that reinterprets the clues we already have. This grand challenge reframes the entire quest. We are not building a ladder to reach a hidden attic. We are listening for the faintest vibrations in the walls of our house, trying to deduce the blueprint of a foundation we may never see directly. The distance between our current understanding and that ultimate goal is the very space where discovery happens. The mathematics of hidden dimensions is a living, breathing frontier. Even as experiments search for their fingerprints, the theoretical landscape itself is shifting beneath our feet, revealing possibilities more profound and strange than we first imagined. One of the most significant steps forward came with a discovery that felt like finding a secret passage between different maps of the same territory. For years, physicists had developed 5 distinct versions of superstring theory, each mathematically valid but seemingly separate. Then, in the 1990s, a deeper insight emerged, suggesting these 5 theories were not rivals, but different perspectives on a single, grander structure. This unifying framework is known as M-theory. It proposes that the true, fundamental reality exists in 11 dimensions, one more than the 10 required by superstring theory. In this picture, the various strings and branes we have discussed are not the final answer, but different manifestations or slices of this 11-dimensional whole. Think of it like this: you can describe water as a liquid, as ice, or as steam. They seem like different substances, but they are all phases of H2O. M-theory suggests that different string theories are like those phases, all emerging from a single, deeper source we are still learning to describe. This unification was a monumental leap, but it came with a humbling twist. We do not yet have a complete set of equations for M-theory itself. It is more of a guiding principle, a map pointing toward a peak we have not yet summited, reminding us that our current understanding is likely still a stepping stone. Alongside this quest for unification, an even more radical idea has emerged from the study of black holes, one that challenges our very notion of what dimensions are. It is called the holographic principle. The story begins with a paradox. When something falls into a black hole, the information that described it, all the details of what made it unique, seems to be lost forever, violating a sacred rule of quantum mechanics. To resolve this, physicists like Leonard Susskind and Gerard T. Hooft proposed a staggering solution. They suggested that all the information about everything within a volume of space, including the complex dance of gravity within it, could be perfectly encoded on the lower dimensional boundary that surrounds it. The most famous example is that a three-dimensional region of space containing a black hole could be completely described by the information painted on its two-dimensional event horizon, the surface of no return. This is not a vague analogy, it is a precise mathematical correspondence. It would be as if the entire rich, three-dimensional world of your living room, the furniture, the air, the light, was nothing more than a highly complex, encrypted movie playing on the flat surface of your walls. The three-dimensional reality you experience would be a projection, an emergent illusion generated from data stored on a lower dimensional screen. This astonishing principle, born at the fiery intersection of black hole physics and string theory, forces us to reimagine the nature of the hidden dimensions we have been searching for. If our universe has a holographic nature, then the extra-spatial dimensions of string theory might not be fundamentally real in the way we intuitively picture them. They may not be little curled-up geometric rooms waiting to be discovered. Instead, they could be emergent properties, computational artifacts that arise from the complex quantum information processing happening on a lower dimensional surface. In this view, dimensions are not the starting point of reality. They are the ending point of our perception. They are how the universe renders itself to itself, a user interface generated by deeper, more fundamental processes that do not require space or time at all. This does not make the search for geometric signatures any less valid. Those signatures would still be real features of our rendered world, clues to the underlying code. But it does mean the ultimate truth might be even stranger than extra curled-up spaces. The holographic principle suggests that the cosmos is not built like a house with hidden rooms, but like a masterpiece painted with a reality so deep, it casts a shadow with more dimensions than the canvas that holds it. Our journey to map the architecture of reality may ultimately lead us to a place where architecture itself is an emergent story, written in a language of information we are only beginning to decipher. The pursuit of knowledge for its own sake has always carried a quiet ethical weight. When we direct immense intellectual and financial resources toward a question as abstract as the existence of hidden dimensions, we are making a profound statement about our values as a civilization. This is not merely a technical challenge, it is a cultural and intellectual imperative. To ask what the universe is truly made of, to seek the foundational blueprint of reality, is to engage in one of the oldest and most defining human endeavors. It is an act of cosmic self-awareness, a way of understanding our own place within the vast, unfolding story of existence. This deep curiosity, this drive to look beyond the horizon of the immediately useful, is what elevates a society. It declares that we are not only concerned with survival and comfort, but with meaning, with legacy, and with the sheer, breathtaking wonder of discovery. The search itself becomes a shared project that transcends borders, uniting scientists from countless nations and backgrounds in a collaborative effort to decode a mystery that belongs to no single country, but to all of humanity. This global cooperation, built on shared data, open publication, and mutual respect, stands as a powerful ethical model in a world often divided, demonstrating that our greatest challenges are best faced together. Yet this noble pursuit does not exist in a vacuum, and its ethical dimensions require honest reflection. The resources dedicated to building a particle collider or a space-based gravitational wave observatory are undeniably vast. It is right and necessary to weigh this investment against other pressing human needs, from health and education to environmental stewardship. The ethical question is not whether to fund one instead of the other, but how to maintain a balanced and wise portfolio of human endeavor. History provides a compelling answer. Time and again, the quest to answer a fundamental question has yielded unforeseen practical rewards. The entire world of digital technology, from transistors to the internet, sprang from our investigation into the puzzling rules of quantum mechanics. The mathematics developed to describe curved spacetime is essential for the GPS systems that guide our travels. The exquisite sensitivity required to hunt for gravitational waves advances medical imaging and materials science. By pushing the absolute boundaries of measurement and computation, fundamental research seeds the technological forests of the future, often in ways no one could have predicted at the outset. Therefore, the most ethical path forward is one of balance and transparency. It is a commitment to supporting a spectrum of research, from the directly applied to the purely exploratory, understanding that they nourish each other in a continuous cycle of inspiration and innovation. The ethical imperative extends to how the knowledge is pursued and shared. This work must be conducted with integrity, its findings communicated openly, and its technological spin-offs guided by a principle of benefit. The tools we forge to listen to the cosmos or to probe the fabric of space should, wherever possible, be directed toward improving life on Earth. The ultimate goal is to ensure that this grand quest remains a noble and inclusive endeavor, one that not only maps the hidden architecture of the universe but also reflects our highest aspirations as a species. It is a declaration that to be human is to look up, to question, and to build a shared understanding that enriches our culture and guides our future with wisdom. These ideas can feel vast, leaving us floating in a sea of abstract possibilities. So let's bring the question home. What does this centuries-long search for hidden dimensions actually mean for you, right now, sitting in your room, looking at your screen? It might seem like a distant puzzle for physicists, but its implications quietly touch the core of how we see our own lives. When you truly absorb the possibility that our solid, tangible world is a projection from a higher dimensional reality, it does something subtle but powerful to your perspective. The stubborn problem you have been wrestling with, the argument that feels so absolute, the seemingly immovable obstacle in your path viewed through this cosmic lens, they begin to change. They are no longer the entire, definitive landscape of your reality, but perhaps just the most immediate shadow on your personal cave wall. This doesn't make them less real, but it can make them feel less final, opening a mental space for creativity and resilience you did not have before. This search is the ultimate expression of a quiet courage we all possess, the courage to doubt the obvious. From the moment a child first wonders why the sky is blue, to the scientist who questions why gravity is so weak, it is the same beautiful impulse. It is the refusal to accept the world as presented, the stubborn belief that there is always a deeper layer of truth, a more elegant story waiting to be uncovered. This journey humbles us in the most profound way. It suggests that our confident senses, our direct experience of a three-dimensional world, is not the final arbiter of what is real. We are built to perceive only a fraction of the symphony, hearing a few notes and trying to guess the composer's full intent. That humility is not a defeat, it is a liberation. It frees us from the arrogance of assuming we already have the complete picture, making us perpetual students of a universe that is always more clever, more strange, and more wonderful than we imagined. Yet, in the same breath, this quest is a towering act of empowerment. It demonstrates that we are not forever trapped by our biological limits. We cannot see the extra dimensions, but we can invent the mathematics to describe them. We cannot touch the quantum foam, but we can design machines to feel its faintest tremors. Through the tools of reason, imagination, and collective effort, we can reach beyond the horizon of our senses. We are building ladders of logic to peer over walls our eyes told us were solid. Whether this specific search ends with a triumphant discovery or gracefully retires in favor of a better idea, its value is already secured. It stands as a testament to the human spirit's deepest desire, not just to live within the cosmos, but to understand it, to look at the silent stars and the bustling world around us and ask, what are the rules? What is the shape of the stage? This relentless curiosity is our species' signature. It is what transforms us from inhabitants of a world into its cartographers, and perhaps one day, its humble confidants, listening as the universe slowly whispers the secrets of its hidden architecture. The hunt is not a single path, but a vast and coordinated net cast across reality itself. From the delicate shiver of a gold plate in a vacuum chamber to the cataclysmic fire of a particle collision, from the ancient whisper of the cosmic microwave background to the silent mathematics on a page, each effort is a different kind of question posed to the universe. Gravity experiments ask if our most familiar force behaves oddly in tiny spaces. Particle colliders ask if energy can vanish into the walls of our dimensional room. Cosmologists ask if the oldest light holds a frozen memory of a more complex geometry. And theorists weave these questions into elegant narratives, mathematical stories that only hold together if the unseen architecture exists. This is the essence of the search, a convergent investigation where no single clue is definitive, but where all must eventually point in the same direction. The compactified curls of string theory and the vast hidden volumes of Brane worlds might seem like competing visions, yet they are not necessarily rivals. They could be different perspectives on the same profound truth, much like describing light as both a wave and a particle. One framework might excel at explaining the quantum nature of forces, while another beautifully solves the puzzle of gravity's weakness. The ultimate theory, should we find it, may incorporate insights from both, revealing a reality where dimensions can be both tightly wound at some scales and expansively hidden at others. This unified picture transforms the scientific endeavor into the greatest detective story ever told. We are presented with a cosmic crime scene, our seemingly complete three-dimensional reality, and we are tasked with reverse engineering the event that created it. Every anomalous measurement, every unexplained constant, every mathematical necessity is a fingerprint or a strand of hair left behind. The detective uses fingerprints, fibers, and witness statements, cross-referencing each piece until a single, coherent narrative emerges. In the same way, physicists must cross-reference the whispers from colliders, the tremors in gravity, the patterns in the sky, and the demands of their equations. Only when these disparate lines of evidence converge, when the gravity experiment, the collider data, and the cosmic map all whisper the same number, the same scale, the same geometric shape, will we have our suspect. This is why the search, for all its philosophical depth, remains grounded in meticulous, often frustrating, empirical work. The elegance of a higher dimensional equation is compelling, but it is not proof. The true unified picture will be painted not by mathematics alone, but by the slow, patient accumulation of clues from every corner of our perception, each one a brushstroke revealing part of a hidden form. We are learning to see with more than our eyes, to feel with more than our hands, assembling a portrait of reality from the faintest impressions it leaves on every instrument we can dream of building. Science rarely follows a straight line drawn on a chalkboard. The story of human discovery is filled with moments where a brilliant mind, looking for one thing, stumbled upon something else entirely, something that changed everything. The search for hidden dimensions, for all its mathematical precision and careful planning, must hold a sacred space for this kind of beautiful accident. We design our experiments to test specific predictions, to hunt for the signatures our theories tell us to expect. But history whispers a crucial reminder: the universe often reveals its deepest truths in ways we never see coming. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were troubleshooting a persistent, annoying hiss in their antenna at Bell Labs. They scrubbed away pigeon droppings, checked every connection, and chased down every possible source of interference, but the faint, uniform static remained. They were not looking for the echo of creation. They were trying to build a better telephone system. That stubborn noise turned out to be the cosmic microwave background radiation, the cooled remnant of the Big Bang's first light, the single most important piece of evidence for our modern understanding of the cosmos. It was a discovery born not from a targeted hypothesis, but from meticulous curiosity about an unexplained anomaly. This is the vital role of serendipity. As we construct ever more sensitive instruments to probe the fabric of reality, we must be prepared for the signal we did not order. It might appear as a tiny, persistent glitch in a tabletop gravity experiment, a measurement that stubbornly refuses to match the expected curve by a minuscule yet undeniable amount. It could be a particle decay event at the Large Hadron Collider that makes no sense within the standard model. A particle that appears and vanishes, leaving an energy signature that simply should not exist. Or it might be a subtle, strange asymmetry in the cosmic microwave background, a pattern that no model of inflation quite explains, a whisper from the ancient geometry of the universe that we lack the vocabulary to interpret. These are not failures, they are potential portals. The moment a scientist leans back from the data, frowns, and says, "That is odd," is often the moment a new chapter of understanding begins. This open-mindedness is the dynamic, living heart of the scientific process. We map out a grand search based on our best theories, drawing up intricate plans to explore the territory we think exists. But reality owes us no allegiance to our maps. The true breakthrough in the hunt for hidden dimensions may not come from confirming an elegant equation for a Calabi-Yau manifold. It may arrive as a baffling piece of data that forces us to throw out our old maps entirely and draft new ones, leading us to a conception of reality we are not yet clever enough to imagine. This intertwining of rigorous planning and readiness for surprise is what keeps the quest alive with a sense of genuine wonder. It means that every graduate student analyzing data, every technician calibrating a sensor, is not just a cog in a machine testing a foregone conclusion. They are a sentinel on the frontier, watching for the flicker of something truly new in the darkness. The search, therefore, becomes a dual journey, one of disciplined focus and of open-ended exploration, reminding us that the cosmos holds its secrets close and sometimes reveals them only when we are wise enough to notice the things we were not looking for. From the quiet mathematical pages of Kaluza-Klein to the colossal detectors listening for gravity's faintest whisper, this has been an epic journey of the human mind. We have traced a path from a simple, elegant idea that a single extra dimension could unify the forces of nature to the sprawling, breathtaking landscapes of string theory and Brane worlds. We have watched as physicists built machines of impossible precision to measure forces smaller than a thought, and listened to the ancient light of the cosmos for echoes of a more complex beginning. This search is far more than a technical puzzle for specialists. It represents a fundamental re-examination of the very stage upon which the universe plays out. We are questioning the most basic assumption of our existence, the three-dimensional reality we navigate with such confidence. The key takeaway from this entire exploration is both humbling and exhilarating. Our direct sensory experience of the world, the solidity of objects, the vastness of space, may be a profound and persistent illusion. It could be just one slice, one shadow, of a richer, more complex reality waiting patiently to be uncovered. The equations suggest it, the experiments hunt for it, and the cosmic clues hint at it. As Carl Sagan so beautifully reminded us, somewhere, something incredible is waiting to be known. That somewhere might be curled up at every point in space or stretched into a vast, hidden bulk just beyond our reach. The search continues, with new experiments coming online and fresh theoretical insights emerging each year. Stay curious, follow the developments in this thrilling field as the greatest detective story ever told unfolds. Share your own thoughts and questions in the comments below, because every mind engaged, every spark of wonder, brings us collectively one step closer to glimpsing the full dimensional truth of our magnificent cosmos.